Dijkstra's.
Who here feels good about Dijkstra's algorithm? Decent, kind of come back. All right, so we'll do just a quick review of Dijkstra's, just because it is kind of relevant to the problem, and then we'll get into minimum spanning trees, and then we'll talk about specifically how those things relate to this problem in particular. So Dijkstra's algorithm is a path-finding algorithm. You have a place that you're starting, and then a place that you're going. And what you do is you just... Oh, it's not? Oh, yep, thank you. Yeah, correct me if I'm wrong. It's been a while since I've done Dijkstra's. Yeah. But you take the node that you're starting at, and you take every edge that it's connected to, and you put them in a queue. But it has to be a priority queue because the next thing you're going to do is take the least edge. And so here, the least edge would be 2. So we take this least edge. And then we take, so we've now made it to this node. And we put every edge that this node is connected to into the priority queue and repeat. So I believe that would, next we would be, I'm not sure what the next thing we do here. I think it'd be a tie between going to this node like this and going to this node like that, because both paths take 3. So it doesn't really matter which path we take. It's the same cost either way. So, but either way, we'd probably go to this node next, because going to this node would require a path of 6. So we're not going to do that. We're going to go to this node. We're going to take every edge that it's connected to, add it to the priority queue. So we've got a 4 here, 7 here. So the next place we're going to go is probably here, I believe. Because in the priority queue, this path is a 6, whereas this path is a 7. So I think we would go here next. Right? Yeah. Something like that. Dijkstra's algorithm is not how you solve the homework problem. I'll just go ahead and say that. So that's why I'm not going into too many details here. I just kind of want to give a general overview of what Dijkstra's algorithm is. It's important to know. And a lot of people have been, the people who have been coming to office hours have been thinking that Dijkstra's algorithm is how you solve the problem. The reason it's not how you solve the problem is that fundamentally Dijkstra's algorithm is looking for a path. So, so far what we've done is we've gone here I'll switch colors here. We've gone here, and then we went here, and then maybe we go here, and here. If you look at just what we've created here, we've created a path, which is super useful, but the homework is asking about clusters. So this is a valid cluster. All paths are clusters, but clusters, not all clusters are paths. So like, here is a valid cluster. We could include this node as well. And then our cluster would be this. That's a valid cluster, but it's not a valid path because what's that? We've got an edge, 2 edges going off to nowhere. So this is a tree. So that's why Dijkstra's is not applicable, is because really clusters are really trees. And Dijkstra's algorithm does not find trees. Well, technically it does find trees, but it doesn't find all trees. It only finds the path trees.
It doesn't find a spanning tree.
Yeah, yes. So that's Dijkstra's algorithm, and that's why it's not applicable. You want to do trims?
Yeah.
Okay.
Should I do it on this graph?
Sure. Here, like copy and paste. Right. You can just like copy, and you can paste, and then you can modify it. So yeah.
All right. So how comfortable do you guys get with trims, just generally? You're pretty good with it? Yeah. Okay. So what prims does is the goal of it is to find a minimum spanning tree, and what that means is a set of the vertices and edges such that the sum of the weights of the edges is the minimum sum, right? So if you have, like, say a very simple example, 1, 2, 3 is your graph. What prim's going to do is it's going to start off by just selecting any node, essentially.
Yeah, because it's a spanning tree, all of the nodes are going to be in the graph at some point. So it doesn't matter which one we start with, because we're going to hit them all.
Yeah. And then so what prims does is it says, okay, from this, so it has a cut here essentially between things in the current spanning tree, and then everything on this side of the cut would be outside of the spanning tree. So it looks, what's the minimum weight edge connecting something inside the tree to something outside the spanning tree? So that's going to be this edge of 1 here. So we're going to select this edge of 1 and bring B into the graph through this edge, right? Now, let's change this. Our cut between the spanning tree and things outside the spanning tree is essentially this cut here, right? What's the shortest edge connecting any node from something inside the cut to outside the cut? So the 2 edges possible are 2 and 3 here. 2 is the shortest one, so we put 2 in the cut, into the tree. And then we end up with this of 1 and 2. And this is a minimum spanning tree because the minimum, or the sum of all the edge weights is 3, and every node is in this spanning tree, right? The reason it's not this is because this would have some sum weights of 5, which is not the minimum, right? So the constraints are that the sums of the edges weights have to be like the minimum possible, and every node must be in the graph. So every node must be in the graph is the spanning part, and the minimum is the minimum part, right? So for this one, on this big graph, let's say we pick this start node here. We're just going to pick the shortest edge leading out of it. It's going to put 2 into the minimum spanning tree. Now the shortest edge leading out of either of these 2 is going to be this 1. So we include this 1 here. Shortest edge connecting a new node would be, so we have 4 here, 7 here, 4 here. Either one is fine, right? If you have 2 equal weight, you just pick one.
Yeah.
And so the reason we don't put this edge 3 into the graph is because it doesn't connect any new node that's not already in the minimum spanning tree, right? So we want every new edge that we put on the graph to connect one that's in the tree to one that's not yet in the tree. So that's why we don't put this edge of 3 in. So let's just pick this one. We're going to put this edge in. The minimum edge weight is now 2. Pick that. Now minimum is 3. So this, I guess I can draw it out a little more clear. So we have this is the subset of the graph that we're looking at. So that's what the minimum spanning tree is going to look like, right? And then sum up all the weights, and you'll see that no matter how you pick a different set of edges that connects all the nodes, the sum of them is not going to be less than this. It could be equal to, like you can have multiple minimum spanning trees that have the same sum. Either one of those is valid. Your prims doesn't guarantee, or prims just finds a minimum spanning tree. It doesn't guarantee that it is the only one. But in some cases, like in this case up here, this is the only minimum spanning tree. Any questions on prims?
It just so happened that this minimum spanning tree kind of looks like a path, but it could have had weird edges, which would have made it not a path. It would have made it a tree.
Yeah. So like say for example, if we made this a weight of 1 instead, how that would have changed our algorithm is we would have connected this one here and then this one here, and then
it's already not a path.
That 3 and then that 2. See, this is not a path because you have 3 nodes coming out of this point here. every edge is coming out of this point.
Questions about Prim's algorithm?
Is there a data structure that relies on like edges?
Yeah, you probably would want to use a priority queue. Yeah, because you've got the set of nodes that are in the tree, or that you've selected so far, and then you have what you're looking for is the minimum edge going from inside the tree so far to outside the tree so far. And so you're going to want to store, to find the minimum quickly, you're going to want a priority queue.
I can step through that a little bit as well. Actually how you do the checking and stuff. So we can use our the same 1, 2, 3. So we pick our start node A, and then we're gonna have like some priority queue, and we look at all of the edges coming out of A. So that's 1, put that on the priority queue, and 3, put that on the priority queue. And then we check, does edge 1 connect something inside to something outside, right? So that could just be, you could have an array that is, so like A, B, and C are the indexes, and say, okay, A is in the tree, B and C are not in the tree. So just like a Boolean array that marks whether or not a given node is in your minimum spanning tree. And then,
Or you could use a hash set or something.
yeah, anything like that. So then you look and see, okay, edge 1 connects B, B is not in. Edge 3 connects C, C is not in, but 1 is less than C, so we're going to add 1 into it, and that would, we change this, because B is now in our minimum spanning tree, and then we would put 2 onto our priority queue. I guess 1 would be off at this point. And then we look at 3 and 2, find that 2 is the shortest one connecting, so 2 connects C, which is not in it, and 3 connects C, which is not in it. Pick the minimum, and then give this one, and then,
Ooh. That's my email.
Bad timing. And yep, now, once all of these are full ones, that means you have your spanning tree, and you can check the minimum here. Cool.
So this is where the textbook might come in handy, because Prim's algorithm is like standard, and so I think the textbook has pretty detailed steps on how to implement it. And that might be useful for the homework.
Yeah, so the thing to keep in mind is that this is a minimum spanning tree, so it finds the minimum sum weights of all the edges. For the homework, you're trying to find the maximum, right? So you can't just use like normal direct prims on that, because prim finds your minimum. So this is something to keep in mind. What's next?
How to do the clustering. If you're moving it.
We're just doing like the heap on a heap.
We're talking about taking the minimum spanning tree and making it into a cluster.
Okay.
We're remembering our plan here.
So let's say that we were given our set of points, right? We put them into some form of prims, right? So this is your modified prims, and this is like we'll black box this for now, and then out comes our maximum spanning tree, right? So this is like, I don't know, like that third part of the homework, kind of. So once you have your minimum spanning tree built, how do you get your clusters, right? That's what this is going to look at. So let's use this same graph. So you built this maximum spanning tree. Is that a good idea?
Hmm?
Like label the edges.
Well, we need to know what the actual weights are.
Yeah.
Or we could just draw it geometrically like we were doing yesterday.
Oh, like the actual points.
Yeah. Here,
Can you just use numbers on the edges?
Hmm?
You just use numbers instead of letters?
Yeah. Well, so in the problem, the weight of the edge is the actual distance between them, which kind of makes it easy to draw the diagrams. Instead of writing out the weights, you can just draw it to scale.
Yeah.
So, like, let's say, let's just say those are our points. And the weight is the distance between them. So let's say the minimum spanning tree is something like, I don't know, let's do something reasonable. Minimum? Let's do minimum.
Oh, okay.
All right, let's say that's the minimum spanning tree. I think that's kind of a reasonable one. Now let's say we wanted to split this graph into two clusters. And since we're dealing with the minimum spanning tree, let's just pretend like the problem is asking for the minimum clusters, just because that's kind of easier to think about. The minimum clusters here, we can kind of visualize them. We just see them by looking. There's one cluster over here, and there's one cluster over here.
What do you mean minimum cluster?
Minimum, so a cluster is yeah, that's a good question. A cluster is a subset of the graph that has minimal edge weights in its spanning tree. So if this is our minimum spanning tree,
A minimal edge weights in this case is distance.
Yeah.
So groups of close together points essentially.
so to split this graph into two clusters, we have to include every point. So we can't just say like the two clusters are this and this. Although those two clusters do have minimal weight, they don't include all the points. We have to include all the points. And the way I think about this is we want to minimize the amount of edge weight in our two clusters. So we want to avoid big edges. So what's the edge we really want to avoid? This one right in the middle, yeah. So we definitely don't want to include that edge. And what have we just done by excluding that edge? Yeah, because we started with a minimum spanning tree, and then we took an edge out, what we're left with now is two minimum spanning trees for two clusters. And so that kind of gives you a hint about how to actually form the clusters. If you have a minimum spanning tree and you take out an edge, what you're left with is the minimum spanning trees of the two clusters.
So then if you take out the next largest edge, then you get the
Yep.
triple?
Yep. So like, let's do it. Let's take out the next largest edge. It's
So because minimum spanning trees don't allow cycles, that pretty much means that every time you remove an edge, you are taking one tree and splitting it into two. So you're adding like a cluster.
yeah. If there were cycles, then
Then you could
get
remove
weird
an edge,
scenarios.
but still have the same number of clusters. But since there's no cycles in the minimum spanning tree, every time you remove an edge, that's creating another cluster, essentially.
So the first part of, I guess, the program would be the same for any number of, like, if you're given to make two clusters in like one cluster, the first part you would have to do it anyways.
If you're given
Do the same way. The first part you do the same
Yeah,
way.
like build a whole structure.
Yeah.
It's not like you're taking into account that you have to build two clusters while you're building.
You don't have to, but you can.
Yeah, there's some optimizations that you can do. I don't think you'll need them to pass the runtime tests. But you can speed it up a little bit by combining the steps.
Yeah.
But you can think of it as just two distinct steps. Build a tree, chop up the tree.
So because a minimum spanning tree, or it has V vertices, right? And since they're all connected, it's always going to have V minus 1 edges, right? Every minimum spanning tree with V nodes has V minus 1 edges. And then to get K clusters, you remove like it's K minus 1 edges, right? Yeah. So if you want 2 clusters, you remove 1 edge. If you want 3 clusters, you can remove 2 edges, right? One optimization that you could do is instead of building out the whole tree and then taking away the K minus 1 edges, just build out the tree until you reach the until you have like V minus 1 minus K edges. So just don't build the whole thing out essentially.
We think that works.
Yeah.
We haven't actually tried it, but we think
Right.
there's some optimization.
Wait,
No one's actually tried it. So
actually no, you can't do that.
I think it works because of the specific changes to the problem. Think about
No, I don't think
what the clusters always are.
because the max.
Yeah.
So
So we haven't tried it, but we
so
think
that doesn't work for any application of a minimum spanning tree, but in this particular homework,
yeah. Some people
there's,
there's a
it
pitfall
does.
with this one. Don't try to visualize the problem. Maximum
Yeah, we
spanning
can-
trees don't make sense, and you don't see them in the real world. There's no reason. We tried for a while to think of a good reason to have a maximum spanning tree,
Yeah.
and could not.
As far as we can tell, there are no like
Yeah.
real world applications
Yeah.
of this.
So we tried for a while. Like we thought maybe it's a taxi driver who was trying to like boost his fares by taking the longest route. No, that doesn't work because that's a route planning. That's not a tree.
Yeah.
So just avoid trying too hard to think about it visually.
Yeah.
Any questions?
If we don't make that optimization, can we still pass the runtime test?
Yeah. We're not even sure if it works. We think it works, but nobody's tried it. So
We just came up with it while like looking over the other solution.
Yeah.
But no, you definitely don't have to do it like that for the homework. It's just if you think about if it makes more sense to you to do it that way, you might want to. But any questions about this or the homework?
or trees, graphs in general. What's the next homework after this? Is it tiling dino?
Not sure.
Yeah, that's all we had. It's kind of a short presentation. I'm sorry we got off to a late start. Feel free to ask us specific questions personally.
Is there gonna do Thursday?
That's what I'm checking right now. I'm not sure.
Stop the recording.
Should we stop the recording? Yeah, we probably should stop the recording. Well, should we? Yeah. I'll edit it later. So not all of the problems we're planning to give are on the schedule here. So there might be one through Thursday. Yeah, I know that there's one Graham's been working on.
But it's like a flow that's
That's the
another
flow.
next.
Tiling dynamics is flow.
Is that
And I don't know. So we're not sure. Yeah, maybe not. I don't know. Ask Graham. Yeah, I don't know.
So, just to clarify, it's okay to take n square just to build the different edges.
Yeah, pretty sure.
Yes.
Yeah, initially.
Because you have to consider every possible edge at some point.
And as you're building out your tree, you still have to look at every single node it connects to find the largest one.
Like
Because one node could be connected to any.
yes.
When you're building a tree,
When you're doing prims on it?
Yeah.
Yeah, Prim's algorithm, I don't think it's gonna quite look at every node for every other node. Because for every, well,
I mean, as
because
you
you don't
go,
have to look at nodes that you've already visited.
you don't have to look at it.
Yeah.
Yeah.
Yeah, if you've built the whole minimum spanning tree except for one node, it's not like you have to take that node and check it against every other. I don't think you do.
But you have the longest edge.
Or maybe you do. If you do, it's unavoidable, and yeah, it's definitely n squared at the runtime at least.
Yeah.
And with prims, as you go, you're already kind of guaranteed that you have like the large the minimum spanning tree at some point. So it's not like if you get farther down the tree, it's like you don't have to like update any other edge, right?
Yeah, so
It
Prim's-
won't, like, what you do later won't change what you had before.
yeah, Prim's algorithm is. Did Graham talk about the greedy algorithm
We
approach?
talked about something like relaxing edges where you would maybe update later on.
No, so this is not one of those problems. It's a greedy problem, which means that the greedy is important. I thought Graham was going to talk about it more. Maybe he will for some other lecture. But a greedy algorithm is one where at some point in the algorithm,
Or at every point.
yeah, at any point in the algorithm, you can tell what the next step is going to be without having to do any work, and you'll be right. You don't have to go back. So the difference between greedy and backtracking, for example, is in backtracking you try everything, and if it didn't work, you go back. In greedy, there's some way to know what the right choice is from the start, from the get-go.
Because you try everything before you make the next step.
No, it's not
No,
because
that
you
would be
tried
backtracking.
everything. So greedy is like, so the algorithm itself is like actually greedy, if you could like personify it, as in it always takes the next immediately best step, right? So for Dijkstra, or for like prims, right? You have your subset of nodes already connected in your minimum spanning tree, and then the rest of them, and you just pick the next shortest one, right? So whichever is the best one is going to have the shortest edge, and that's guaranteed to be like a correct solution, taking the next shortest one. So the one that like takes you closest to your goal will work. And so that school of thought only works on problems, on algorithms where like greedy works.
So like the classic example of a greedy algorithm is figuring out the minimum number of coins you need to add up to a certain number of cents. So if we have like 86 cents, we could try every combination of coins and backtrack if we don't add up to the sum or something like that.
But you
But-
always know that it's going to have at
But
least
yeah,
3/4.
the minimum number of coins is going to include the most number of big
of the large
coins.
ones.
So we're just going to go ahead and get ourselves up to 75 cents by just including 3 quarters. And then we're only left with what, 11 cents? So we're definitely going to include a dime and that's 10. So that was greedy. We didn't have to do any backtracking. We didn't have to change our solution later. We just, at every step, we know what the right thing to do is.
And the next topic that you're going to do is max flow, right? And that is a lot of go forward, progress, and then if you discover you can't go further, change what you did back at the beginning.
So max flow is not
So-
greedy.
Max flow is not greedy,
Is
and
that more backtracking?
it's more similar to backtracking, but
It's not
quite
strictly
backtracking.
backtracking. No. It's kind of its own thing.
It's its own thing. But yeah, you'll talk about that in lecture probably this week, or next week.
Probably this week. Yeah. Well, I thought there was already a lecture on it.
Oh,
Yeah, I think.
Yeah.
Oh,
yeah.
okay.
Yeah, greedy's good to know about, especially if you try to do Alex's bonus problem, which straight up admits that it's a greedy problem. Yeah, cool.
Wait, so building the tree, like when they have the point to insert, do we just connect that point to every other point that currently exists at the beginning? And then we do the maximum spanning tree from that?
Yeah, pretty much.
You don't connect it to every point that already exists. You just connect it to the edge that's closest, or the.
No, when you're initially building the graph with the points, you connect all points to each other.
Oh yeah, yeah. The graph at the beginning, like if I kind of, yeah.
The graph that you run prims on is just every point connected to each other.
Yeah, I skipped that step earlier, but the graph here would be this. every possible. I don't really. Should
And it doesn't matter how we represent the graph, either like 2D matrix.
Shouldn't. Yeah. I doubt that would. Like the only possible problem would be the time constraint, but I don't think that would be enough, would it?
We don't have to use one of the data structures that was provided in the slides, like the edge weight.
Oh. Yeah, those are just. Like you don't have to use them, but some of them provide kind of like useful functionality that might just make it simpler for you. But like, you shouldn't get into trouble if you don't use them, as long as you're like not inefficient in what you're doing instead.
Yeah, I'll check on that.
I think Prims typically uses a priority queue. Or is it? No. Yeah. Do any of these use a heap, or is that?
It looks like I think what Graham used is an adjacency list.
Yeah.
I think you could probably do it better than that, even just because you already know every possible edge exists. So you could probably use nothing. You could probably not store the edges at all because you already know they exist. All you'd have to store are the edges that you've chosen as part of your minimum spanning tree. So for that, you probably would want to use an adjacency list or something. But as far as setting up the initial graph, I wouldn't set it up at all.
Are adjacency lists better when like edges are close to max edges?
No, adjacency lists are better for sparse graphs, which is minimum spanning trees are sparse.
Yeah, but fully controlled.
Yeah, that's why I'm saying I wouldn't put the graph with all the edges in an adjacency list. That would be slow. But it looks like that's what Graham is doing, so probably doesn't matter. Yeah.
And Prim's algorithm uses like heap.
Yeah.
Does it?
Yeah. Priority queue.
Oh,
There's a priority queue class in Java. So I recommend using that.
And would that
Don't implement heap.
contain pretty much every possible node since it is connected to?
The priority queue contains
contains the edges that you're looking at.
Yeah.
So you take, like you pick your starting node, and then every edge coming out of that starting node you put into a priority, like a min heap. And then min heap, you just take the min, and then, or take like, the top of the head. What's it called? Min heap.
Min.
So yeah, you just like take the min out of the min heap, and that's going to be the least weight edge coming out of that node. Then you check to connect something that's not in the graph to something that's in the tree. Right? And then you add it to your spanning tree, and you can like take it out of the heap. Right? And then like from that new node, you add all the edges coming out of that to the heap. And then so in the heap is now the edges from the second node and the edges from the first node. So you take the minimum from either of those, right? And you just need to do it. So what goes on the heap is the edges that you're like that are in consideration so far.
Okay. And that's constant time to determine where to connect next.
Yes.
Yeah.
So yeah, adding the edges is a log number of edges you have, but yeah, determining the next one to put in is constant.
Yeah, I would totally check out the textbook. I think I've heard it has very detailed steps on prims.
Is the textbook online?
Yeah, I think I don't know. Is the textbook online? It is online. Yeah, I've heard it's online, and apparently,
I had never looked at it before.
honestly, me neither. But I've just heard it's good.
It's like on the bottom of the slide.
Okay.
Have you looked at that? All right. Stop this recording.